Let's talk about building things. Whether it's a simple prop or a jet engine, it all starts with a plan, a drawing. In engineering, we use standard views, top, front and right side, to show height, width and depth. For basic shapes, that's enough. But most real-world objects aren't just blocks or spheres. They have slanted surfaces, angled holes and curves that don't fit neatly into standard views. Try to show a slanted surface with just those views, and you get distortion, like describing a spiral staircase from above or the side. You miss the true shape and size, which leads to mistakes in manufacturing. If a drawing distorts a hole on an angled bracket, how do you know its real diameter or where to drill? You don't, you guess, and that's risky. We need a way to see tricky surfaces head-on to reveal their true shape. That's where auxiliary views come in. An auxiliary view lets you walk around the object and look straight at a slanted face. It unfolds the object, showing the real, undistorted shape and size of angled features. For complex parts, auxiliary views aren't optional, they're essential. They're the difference between a part that fits and one that ends up as scrap. That's why every engineer and machinist needs to master them. So, what is an auxiliary view? It's an extra projection, drawn in addition to the standard top, front, and side views. The key, it's projected onto a plane parallel to the slanted surface you want to see. Imagine a box with a lid propped open at 45 degrees. From the top, the lid looks short. From the front, it's a line. Neither shows its true size. But if you look straight at the lid, perpendicular to its surface, you see its real shape. That's what an auxiliary view does. It eliminates distortion or foreshortening by showing the true size and shape of an angled surface. Features like holes or edges appear exactly as they are. No more guessing. A circle on a slanted face, which looks like an ellipse in standard views, appears as a perfect circle in the auxiliary view. We use projection lines drawn perpendicular from the slanted surface in a standard view to map features onto the auxiliary view. Then, we transfer depth from another standard view to complete the picture. It's a logical, systematic way to unfold a 3D object onto paper without losing critical information. Auxiliary views are the key to clarity in technical drawings. They make sure nothing gets lost in translation. That's why they're so powerful. When do you need an auxiliary view? Anytime a part has a key feature on a surface that isn't parallel to the main planes. Think of a bracket with a hole drilled at a 30-degree angle. In standard views, that hole looks like an oval, useless for manufacturing. An auxiliary view projects perpendicular to the slanted surface, showing the hole as a true circle with its real diameter and position. No ambiguity, no guesswork, just accuracy. This is vital for parts that must fit together perfectly, like dovetail slides in machine tools. Dovetails have angled sides. Only an auxiliary view shows their true profile for precise machining. For complex parts, like turbine blades or heat sink fins, auxiliary views are the only way to show the true shape and dimensions of angled features. Without them, you're left with a confusing mess of lines and distorted shapes. Auxiliary views turn that mess into clear, actionable information. They're the only way to communicate complex geometry to the shop floor. That's how you get parts that work, every time. If you want precision, you need auxiliary views. Standard views just aren't enough. Auxiliary views give us 3 superpowers: accuracy, clarity, and error prevention. First, accuracy. Dimensions on an auxiliary view are true, not distorted. Machinists can trust what they see. Second, clarity. Auxiliary views isolate complex features, making drawings easy to read and interpret. No more confusion or wasted time trying to decipher foreshortened shapes. Third, error prevention. Clear drawings mean fewer mistakes, less wasted material, and safer, more reliable products. In global manufacturing, everyone speaks the language of engineering drawings. A well-drawn auxiliary view is understood anywhere, without long notes or translations. It's a graphical solution that ensures everyone, from designer to machinist, sees the same thing. That's how you build things right, every time. Auxiliary views are the backbone of precision manufacturing. They make sure nothing gets lost in translation. Let's get technical. There are two main types of auxiliary views: primary and secondary. A primary auxiliary view is used for a surface inclined to two principal planes but perpendicular to the third. For example, a ramp on a block, angled to the top and front but perpendicular to the side. You project from a standard view, set up a new viewing plane parallel to the inclined surface, and use a folding line as your hinge. This reveals the true shape of the angled surface. But what if the surface is slanted in every direction? An oblique surface? Then you need a secondary auxiliary view. First, create a primary auxiliary view to show the oblique surface as a line. Then, project a second auxiliary view from that line, parallel to the surface. Only then do you see the true shape of the most complex surfaces. It's a two-step process for the trickiest geometry. That's how you handle even the wildest shapes. Let's draw a primary auxiliary view, step by step. Start with your standard views, front and top. In the front view, the slanted surface appears as an angled line. In the top, it's foreshortened. Draw a reference plane line parallel to the angled edge in the front view. This is your folding line. From every key point on the slanted surface, draw projection lines perpendicular to the folding line. These lines map features from the front view into the auxiliary view. Next, transfer depth from the top view, measure the distance from the reference plane to each feature, and mark it along the corresponding projection line in the auxiliary view. Connect the dots, and you reveal the true, undistorted shape of the slanted surface. Holes appear as perfect circles, edges as true lines. This method guarantees accuracy and clarity. It's a logical process, no guesswork. With practice, it becomes second nature. That's how you turn complex geometry into clear, buildable drawings. Auxiliary views make it possible. Auxiliary views aren't just theory. They're used to build real-world marvels. Take a cam in an engine. Its precise profile controls timing and performance. Standard views can't show its true shape, but an auxiliary view does, allowing for perfect machining. Or a bevel gear. Its teeth are complex, changing shape along their length. Only an auxiliary view, projected along the gear's axis, defines the tooth profile for smooth operation. In aerospace, jet fighters are full of oblique surfaces. The wing fuselage joint is a complex curve. Auxiliary views reveal the true shape for perfect assembly. These views are the hidden language behind high-performance machines. Without them, modern engineering wouldn't be possible. They turn imagination into reality. That's the power of auxiliary views. The big takeaway: auxiliary views are more than just drawings. They're the bridge between imagination and reality. They translate complex 3D ideas into clear, buildable instructions. Even in the digital age, these principles underpin how 3D models become 2D shop drawings. Learning to create and read auxiliary views sharpens your understanding of geometry and manufacturing. It's a skill every builder, engineer, and maker needs. Auxiliary views eliminate ambiguity and ensure precision. They're the secret to turning plans into perfect parts. Next time you see a complex object, remember the humble auxiliary view. It's the unsung hero of engineering, making bold ideas real. That's what making things is all about.